Okay, so today, so the first lecture was basically symmetric groups and Coxeter groups and affine reflection groups. Then the last lecture we did the Kazhdan-Lusztig basis and the Coxeter complex. And today I want to discuss Bruhat graphs and something called the Combinatorial invariance conjecture, which has fascinated me since I was a PhD student, but I'm not really sure why. I'm not convinced it's particularly important. I just think it's really nice. Okay. So I want to, as always, begin with a quote. So this quote is from Robert Langlands. My own mathematical experience and observation strongly suggest that progress is almost always the result of sustained awareness of the principal issues supplemented by some specific concrete insight, begged, borrowed, or stolen, or, happiest of all, distilled in one's own alembic. I offer no insights. So this is from a beautiful paper called Where Stands Functoriality Today? And as a PhD student, I had this up on my wall. I found it really inspiring. And I think it's a nice message to keep in your mind what you see as important and not simply enough to think that something's important and worth solving. You need some specific little in. So I think most mathematicians have 20 problems they would love to solve, and 19 or 20 of them, they have no particular way of solving them currently. And whenever you learn a new technique, you think, oh, maybe that's a concrete insight for one of my problems. So an example of this is the fact that I'm interested in this combinatorial invariance conjecture, but I never had an in. And then when I learned about this machine learning business that I'll talk about tomorrow night in the public lecture, I thought, oh, maybe this is some way of attacking this problem that I've had no idea how to attack. Okay. But anyway, I find this also alembic. Does anyone know what alembic is? The little.
Like a little glass device used for, I guess, chemistry.
Yeah, exactly. So Anna said an alembic is a little glass device that you use for chemistry. And my understanding of the term alembic is it's very much kind of got connotations of alchemy. So it's the flasks in which you conduct alchemy. Okay. And I think it's a beautiful image, your own alembic at home where you're experimenting with the potions. Okay. So firstly, I want to introduce the Bruhat graph. Also, I just want to, just for this lecture, so I'm telling you about combinatorial invariance, which I think is fascinating. And also, this is an open conjecture, it's unsolved, and I don't really think we know how to think about it. Okay. So all I'm trying to do is give you a sequence of clues. And I feel like we found a big clue for the symmetric group, which I'll discuss on Friday, but we still don't really know what's going on. So I'm kind of presenting, potential clues on this problem, but I don't know what the final outcome is going to be. So the Bruhat graph is an incredibly important basic graph associated to a Coxeter group, where I take vertices, all of my elements of W, and then I draw an edge between two elements whenever they're related by reflections. Okay. So you might say to me, that doesn't sound very special. This is just the Cayley graph of a Coxeter group where I'm taking the reflections as generators. And that's entirely correct. The only thing that's subtle here is this direction. So we have a directed edge from X to TX if the length goes down. So as an undirected graph, this is simple. As a directed graph, it's complicated. Particularly its directed subgraphs are very complicated. So in the exercises, we saw that Bruhat order is precisely generated by what I've written in point 2 there. So X is less than or equal to Y if I can find a chain down in my group going from Y to X, where at each point I multiply by a reflection and decrease length. So that alternative characterization is telling me that in this big Bruhat graph, so here's a picture of the Bruhat graph for S3. So in this graph, x is less than or equal to y if I can find the path from y down to x in the Bruhat graph. Okay. And there's this issue of labeling, which is kind of comes up again and again. So the edges of the Bruhat graph are labeled by reflections. We can label the Bruhat graph if we wish. Good?
Should there be a arrow from ST to the NX?
Good question. What's the answer? So apologies why. So Fern is asking, should there be an arrow here? What do you think?
Oh, that's not a question.
Yeah, ST is not a reflection. Yeah. So you're absolutely right that there's a covering, so not a covering relation, but identity is less than ST in Bruhat order. I don't know why that's not showing up. Okay, so identity is less than ST in Bruhat order, but we don't have an edge because there's no direct route in this Bruhat graph. Huh? So no, and the reason is simple. Yes. So the question was, do we fix the left or right action? And maybe I can ask you why we don't. You don't have to, but I would say not because of the rate relation. So if Tx, so if we have an arrow like this, then we can also write this as, how do we write it again? X times X inverse Tx. Okay, and this is again reflection because it's a conjugate of a reflection. Yeah. So it's a good question whether we do this on the left or the right. And the labeling depends on whether we do it on the left or the right, but we get the same graph whether we, independent of the direction that we do it. That's a good question for another reason. So, and we could consider another order where we only allow simple reflections. We only allow elements of S rather than T. So that's very important. So we could only allow elements of S or, on the left or on the right. And then we get two different orders, which are actually distinct, whether we do it on the left or the right. And these are called the left weak and the right weak orders. Okay. And it's probably important to realize, this is something that confused me a lot as a PhD student, that I can have covering relations in Bruhat order, which are not covering relations in weak order, in either weak or right, left or right order. Okay, so there's strictly more relations in Bruhat order than there are in left or right weak order. And also somehow Bruhat order is very complicated. Left weak or right weak order is much simpler. It's lattice, and combinatorial much simpler. So Bruhat order is what we really care about. Gaston? I'm missing 3 labels, but that's your job to fill them in. Okay? I'm not labeling all the edges. So Gaston pointed out that I'm missing 3 labels, which is indeed correct. Okay, so Bruhat graph of an interval. So if I take x and y, I can consider the interval of elements between x and y. Okay, so this is all the elements that I can get to on a voyage from y down to x in my Bruhat graph. So this is just a full subgraph with these vertices. So here's my Bruhat graph of S3, and you can see that there's, got no idea why my pointer's not working today. I've never had this before. Maybe I'll. Yeah, it's a mystery. No idea. Okay, so I'm pointerless today. so on the right, we see the Bruhat graph of the full interval, and you can see the subgraphs of intervals that you get. And although there's many intervals, we see a small number of subgraphs showing up. And also, if we have an edge labeling of the full graph, of course, we can get an edge labeling on the subgraph if we want. So I want to emphasize that this edge labeling is there, but sometimes we consider it, sometimes we don't. Okay, so here's the combinatorial invariance conjecture. What it says is that if we have an isomorphism of directed graphs for two intervals in any two Coxeter systems, so I take two potentially totally different Coxeter systems, I take two intervals, I look at the Bruhat graphs of the intervals from x to y and x prime to y prime in these two different Coxeter groups. If the graphs are isomorphic, then the Kazhdan-Lusztig polynomials are isomorphic. So equal. Okay. So this conjecture was stated first in print by Matthew Dyer in his PhD thesis, which was written at the University of Sydney in about 1989. So Matthew Dyer has this interesting story about his thesis. So his thesis is incredibly inspiring for me. And he was working away. And at that point, this was the time before wide use of computers, and people didn't have access to, you couldn't just have a computer and type up your thesis in tech. And he got a scholarship for someone to type his thesis. So this was like a few $1,000s that would pay someone to type his thesis. And he was regularly sending this person chapters of his thesis, and the person was meant to be typing them. And then about 2 days before he was meant to submit his thesis and leave for MIT, where he had a postdoc, this person rang him up and said, was basically having a nervous breakdown and said, I never knew how to LaTeX, I was just taking the money. I've written nothing. And Matthew Dyer's like, oh, geez, that's interesting. I have about 2 days to submit this thesis. And Matthew said that he just went into a room and taught himself LaTeX and typed the whole thing down over like a 48-hour period, and then submitted the thesis. Okay. Totally amazing. And then got on the plane, and his thesis, like, you know, it's very, very few typos as far as I can make out, and incredible amount of content. Yeah? So he states this conjecture in his thesis. And then when it became widely known, Lustig said, oh, by the way, everyone, I noticed this in 1981 or something. Here's some unpublished evidence that I already knew about this conjecture. Okay, so it's known as the Lustig-Dyer combinatorial invariance conjecture. And yeah, maybe to say one more time, like I'm not convinced this is, you know, it just seems interesting to me. I don't, you know, it may not be particularly deep or whatever. I just like it. Yeah, Masood.
Is there a reformulation of this conjecture in terms of geometry of Schubert?
So Masood asked, is there a reformulation of this conjecture in terms of the geometry of Schubert varieties? And there is, which is, like, as we'll see in tomorrow's lecture, Kazhdan-Lusztig polynomials provide very subtle invariance of singularities in Schubert varieties. So you have certain algebraic varieties, which we might have met in Ting's course and we'll meet tomorrow. They have certain singularities, and I can ask for a measurement of how singular these are, which is called local intersection cohomology, and Kazhdan-Lusztig polynomials are measuring that. Now, imagine that I go to an algebraic geometer and I say, I want to work out the local intersection cohomology of this variety. And they say, oh, sure. What variety are you looking at? And then you say to them, no, I'm not going to tell you what variety I'm looking at. I'm just going to tell you like an extreme combinatorial skeleton of this variety. Namely, I'm going to say it has certain affine spaces, and these are their closure relations between them. Then, with high probability, the algebraic geometer would tell you to go and jump in a lake. Yeah? But the combinatorial invariance conjecture is saying that you can work out these subtle invariance of singularities from very limited information about the structure of the space. Yeah? So the first remark, so I'll make the kind of easy remarks on this conjecture. So the first one, is that we've seen that Kazhdan-Lusztig polynomials are non-zero if and only if x is less than or equal to y, which is the case if and only if the Bruhat graph is not empty. Okay, so that's a first very basic consistency check. There's a beautiful theorem, which is now actually really a theorem, it's not obvious, which tells you that the Kazhdan-Lusztig polynomial is 1 if and only if the Bruhat graph is regular when I forget the direction. So I have a directed graph. I forget that it's a directed graph. I forget the directions on the edges. If every vertex has the same degree everywhere, then my Kazhdan-Lusztig polynomial is 1. Okay. And that strikes me, like that's an incredibly beautiful basic statement. Yeah. Another thing, this is also proved in Dyer's thesis, is that you can, if I just give you Bruhat order, you can get back the Bruhat graph. It's very important. So I do the following procedure. So whenever I see a configuration, a subgraph isomorphic to the thing that I've drawn, I add a long edge, and then I repeat. It's a subtle point. So basically, the combinatorial invariance conjecture can be stated as if the intervals in Bruhat order between x and y and x prime and y prime are isomorphic as intervals, as posets, then the Kazhdan-Lusztig polynomials are the same. And that fits into what I was saying in response to Masood's question about if I just know the closure relations between certain strata, then I know Bruhat order. No, then I know the Bruhat graph, apologies. It's a charming test of how well we understand Kazhdan-Lusztig polynomials. I would say if we can't solve this conjecture, we don't understand Kazhdan-Lusztig polynomials particularly well. But it shouldn't be taken too seriously. So here's an example. This is the first example that you see. So yesterday we were computing Kazhdan-Lusztig polynomials in this land of the Coxeter complex, which is kind of different to Bruhat graph land. But I'll give you two intervals. So this is actually two examples that we saw yesterday. So in both of these cases, we get isomorphic intervals. We get something, so that's a beautiful Bruhat graph known as a 4-crown. And in both cases, we get v plus v cubed as the Kazhdan-Lusztig polynomial. And so this is evidence for the conjecture. Yeah, so I should just be able to see, when I was a PhD student, I kind of computed the Kazhdan-Lusztig polynomial on the left, and I computed the Kazhdan-Lusztig polynomial on the right, and I saw that they're the same, and I was trying to find a good reason for them to be the same. And this is kind of some reason why they're the same. Yeah, the intervals are isomorphic, if you believe the conjecture. Yeah, so for the experts, so we understand Bruhat intervals of small length rather well, and this is an example of a 4-crown. And if you, like a 3-crown would be, so you can draw an n-crown by going duck, 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 duck. So this would be an example of an n-crown. And the Kazhdan-Lusztig polynomial for an n-crown is always like the coefficient of v gives you the n minus 3 for the n-crown. So if we did a 3-crown, we'd get something like this picture. So this would be a 3-crown. And here the Kazhdan-Lusztig polynomial is v cubed. And can someone reconcile that with something that I said earlier? Exactly. It's 3 regular. Yeah. And so kind of beautiful, yeah? So now I want to explain a brief but important point. So this is just a series of clues about the conjecture. So the first one is that the combinatorial invariance for the Kazhdan-Lusztig polynomials is the same thing as the combinatorial invariance for the R-polynomials. So the R-polynomials are what happened when I invert delta y. when I apply the bar involution to delta y, I get all these polynomials. These are the R-polynomials. And basically, if we can read R-polynomials off the Bruhat graph, then we can read Kazhdan-Lusztig polynomials off the Bruhat graph. And this seems like a simplification because R-polynomials are much simpler. It appears. So let me explain why that is the case. This is a simple thing that I can explain on a slide. So before I explain this way of constructing Kazhdan-Lusztig polynomials, which kind of starts at the identity and slowly works your way up. There's a much more complicated way of computing these, where you start from the top, you fix your y and you work down. And one never does this in practice because it's a pain in the neck to do in practice, basically. But it is useful theoretically, as we'll see from the following argument. So what we do is we take the fact that the Kazhdan-Lusztig basis is self-dual. And let's just expand this in a totally naive way. So firstly, here I'm just rewriting the Kazhdan-Lusztig basis in its definition with Kazhdan-Lusztig polynomials. And so now I want to just apply bar to the right-hand term. So we apply bar to the right-hand term. So this is really annoying me that my pointer is not. No one has any idea why it's not working? Okay, such is life. So maybe I can just use a color. So if we expand this term here, we get like hzy times delta z bar, and delta z bar expands into terms of a whole lot of R polynomials. So if we expand that right-hand side and take coefficients of delta x, we get the following identity. So I'm not doing anything fancy here. And now, if you believe that you're starting from the top and working your way down, almost everything in this formula is known. So a Kazhdan-Lusztig polynomial between some intermediate point on the top is known by induction, as is an R polynomial going down, because that's also a smaller interval. So the only missing term in this equation is Rxy, namely the Kazhdan-Lusztig polynomial right up to the top. Okay. And notice, like we get so when we rearrange this formula, we get a beautiful thing. So on the left-hand side, we have hyx minus hyx bar. So hyx is a polynomial in V without constant term, and hyx bar is then a polynomial in V inverse without constant term. So there's no cancellation when we subtract one from the other. And so if we knew Rxy, we'd know everything by induction. Okay, so I want to give what's probably the most general thing known about the combinatorial invariance conjecture, which is this beautiful formula of Dyer, where he gets the R polynomial from the Bruhat graph with a little bit of source, namely the labeling by the reflections. But in order to do that, I first need to explain the formula of Deodhar. So this is also a beautiful formula. And if you did the exercises yesterday, this was one of the exercises. Also, I'm just so delighted to see everyone doing the exercises. So normally at these things, I kind of say to everyone, you should do the exercises, but everyone seems to be doing the exercises. So I'm very happy. So remember, when we have a sub-expression, I like to think about this as a walk through the Cox-Theta group, where we start at the identity and then we go S1, S1, S2, S1, S2, S3, etc. And then, so that's an expression, gives me a walk. And then a sub-expression is like, I get directions to go in the Cox-Theta group, and I either follow these directions or I stay where I am. Yeah? And we can label our sub-expression by kind of up or down, where in each point we say whether we would go up or down if we followed that instruction. Okay. So you can imagine that someone's like telling you, you should, make an S move. And then you decide whether you do make that S move or not. And when you make that decision, you also remember whether you would have gone up or down in following that S move. Okay, so here's two examples, STS, our favorite example. So 1, 0, 0. So that means we go, so, you know, our instruction is S, we go, okay. Then the instruction is T, and we say, no, I'm staying where I am. But if we had followed T, we would have gone up. So we get an up arrow, we get an up label. And then the next instruction is S, and I'm currently at S. So if I was multiplied by S, I would go down. And so then I get this labeling up, up, down. Yeah. Whereas if I took the other expression, 0, 0, 1, so this means the first instruction would be go to S, and I say no. Go to T, I say no. And then go to S, and I say yes. Yeah. And so this is like, would have gone up, would have gone up, would have gone up, and do go up. Yeah. So that's an up, up, up. So this is the way that this is kind of notation that Ben Elias and I started using, and it's seems to be super useful. Like, okay, so what's Deodhar's lovely formula? It says we fix a reduced expression for y. So we want to compute this R polynomial, Rxy. We fix a reduced expression for y, and then we sum over all sub-expressions with n point. So I should have said with n point x that have no down zeros. So that means that if the instruction is you're going down, you have to go down. You can't say no. If the instruction is go up, you can decide whether you go up or not. If the instruction is go down, you have to go down. That's what no down zeros means. Okay. And the R polynomial is just a simple sum over V minus V inverse to the number of zeros in E, i.e. the number of times you haven't followed the instruction to go up. So in the exercises today, we'll see that in the language of kind of galleries and things, this is the statement that a gallery should be positively folded. So if that speaks to you, there's a nice exercise about that. Okay, so if we look at the R polynomial from the identity to STS, so this is so there's two sub-expressions. So we have, so here's our word STS. There's two sub-expressions for the identity, 0, 0, 0, and where we go up at S and back down again. And these both do not have down zeros. So every time there's an instruction to go down, I do. And so I get two terms in my sum. Whereas S, this R polynomial here, there's two sub-expressions for S, but one of them is forbidden because it has a down zero. The one, so there's, I say no 1, 0, 0, because that means I go up to S, and then T, I would have gone up and I don't, that's fine. But then the final one, the instruction is S. So if I followed that, I would go down. So I have to go down. I'm not allowed to say no. Okay. So that's Deodhar's formula. Now we have Dyer's formula. So yeah, maybe so Deodhar's formula is very nice, but it really depends on this reduced expression from Y, the reduced expression starting at the identity all the way up to Y. So if I think about the combinatorial invariance conjecture, I think about, I have some element Y that's very, very far from the identity, and my X might be quite close to Y. And so the fact that Deodhar's formula involves this journey all the way from identity up to Y means that it's not so useful for attacking combinatorial invariance. Now I want to explain a beautiful reformulation of Deodhar's formula due to Dyer. So I think he found it in a completely different way, but you can see it as like a repackaging of Deodhar's formula, which actually just takes place in that interval of elements between X and Y. So if we have a reduced expression for Y, we can consider so these are all of the, so one way of thinking about this is if we want to think algebraically, this is all of the reflections which we would left multiply to do our journey. So we're doing our journey from identity up to y via right multiplication. If we repackage this in terms of left multiplication by reflections, then this would be the account of our journey in reflections. Another way of thinking about it geometrically in terms of the Coxeter complex is as I go from my journey from identity up to y, I'm crossing various hyperplanes and I'm recording which hyperplanes I'm crossing. So I get this order. T1 is less than T2 is less than T3 is less than Tm. Now this order appears like with time, it turns out to have miraculous kind of properties. So Deodhar's beautiful formula, sorry, Dyer's beautiful formula is I look, so this entirely stays in the interval between X and Y, and I look at paths from Y down to X, which are decreasing in this funny order that I just wrote above. So I have my interval, and then I have this labeling of the edges via reflections, and I want to take, for example, maybe first I take Tm, and then I'm allowed to take T3, but once I've taken T3, I'm not allowed to take any other reflection T4, T5, T6, then I've got to take T2 or T1. So here's two examples. Okay, here's S3 again. Now, my order from the reduced expression STS tells me that S is less than the reflection STS, which is less than the reflection T. And so over here, there's 3 different decreasing paths down to here. Okay. But only 2 of them are allowed because I'm allowed to go T, STS, S, that's decreasing in this order. And I'm allowed to just take STS, the direct route home, but I'm not allowed to go S, STS, T. Okay. That's true. Absolutely. Yeah, I have way more paths, of course. So I can also go like this, etc. But none of these are decreasing either. Thanks, Gaston. Yeah, so so Gaston pointed out that there's, of course, there's a hell of a lot of paths from the top to the bottom, but I claim that only 2 of them are decreasing in this order. Kind of remarkable. So what this tells us is that combinatorial invariance is true if we can somehow recover this labeling of our edges by reflections. But that's very hard to do, and I don't really believe it's possible after looking at a whole lot of examples. Yes, Joel?
I suppose you get an order on some reflections. So how do you interpret that in the graph? Like you can't use the reflections.
So that's a really good question. So Joel's saying you get an order on some reflections. It's a very good point. Am I only allowed to use the reflections that happen to be on my list? But actually, unless I made a howling error this morning, all the labels on the Bruhat interval less than or equal to y are on my list. Gaston gives me a thumbs up. Yep. Okay, that's an extremely important point. Yeah. So I've just told you how to order some set of reflections, but in fact, everything that shows up in my interval is on my list, so this makes sense. Yeah. So that's also on the exercises today. Okay, I really love this formula. So consequences of Dyer's formula. So if we have the ordering, so these orderings that show up might look kind of arbitrary, but they're very important in Lie theory. They're called convex orderings. I'll discuss them briefly in a second, but I'm just saying the obvious. If we know the Bruhat graph and the edge labelings, we can recover the Kazhdan-Lusztig polynomial. Another beautiful thing is that if we look at maximal chains, so paths where we never take a long edge, then within every maximal chain, there's a unique funny order decreasing path. And what that tells us is that if there's no long edges, then the only decreasing path is this one. So that tells you that the R polynomial is very simple, V minus V inverse. And so that tells you that if the Bruhat graph has no long edges, combinatorial invariance is true. And this actually covers like a very large number of examples. Yeah. So in symmetric groups, you can find like hundreds of millions of examples with no long edges. Okay. And it's true for all of them. No. So the four crowns are a classic example of something with no long edges. Yeah. There's no long edges in the N crown. Okay, so if you want to hear something kind of fancy, my feeling is that no long edges is kind of that the Schubert variety is close enough to toric land, the world of toric varieties. So this formula for the R polynomial, if you do it in the world of toric varieties, it recovers something called the Kazhdan-Lusztig polynomial, which is very important invariance of convex polytopes. And yeah, the theory is much simpler, and in some sense, it's like there's a part of Schubert varieties that looks like that much simpler theory. So convex orderings, I'll just go over this briefly for interested experts. So the orderings, so these are convex orderings, and the key condition is that in any dihedral reflection subgroup, so this is any subgroup of any subgroup generated by two reflections is a dihedral reflection subgroup. In any such subgroup, it makes sense to talk about what S and T is. I haven't gone into reflection subgroups at all, but you can either take the reflections kind of, like if you think about a dihedral root system, you have your two simple roots and then you have a whole lot of roots. And your reflection order either goes like that or like that. So that's the condition on a convex ordering. And the beautiful fact, W for finite Coxeter groups, convex ordering is exactly the same thing as a reduced expression for the longest element. So what that tells you is that you can kind of think about convex orderings, these things showing up as something like a reduced expression for the longest element, even though the longest element might not exist. And there's this fascinating world of convex orderings on infinite Coxeter groups, and they play some kind of role of like a reduced expression for the longest element, even though that element does not exist. I just want to explain briefly why I think this problem is very subtle, and also kind of explains to a large extent why I find it so interesting. So we went over this geometric representation. Okay, so the symmetric group has this beautiful representation on an n-1 dimensional space where each reflection acts as a reflection. And what I can do is I can just like and I always think about this natural representation as a quotient. And what I can do is just like, if I take the vector 1, 2 up to n and I act on it by x, then I get exactly the string notation of my permutation. Yeah, so it's a nice little like geometric encoding of something combinatorial. And if I have, so this embeds my Bruhat graph in a very nice way in this n-1 dimensional space. So it embeds it in such a way that edges in my Bruhat graph, so the edge labeled by a reflection, points in the direction of the corresponding root. So it's a very nice embedding. And if we have this embedding, we can recover the Kazhdan-Lusztig polynomial. So I won't go into that, but that's essentially follows from Dyer's formula. Like if we have this embedding, then we know enough about directions that we can tell reflections and things like that. And what seems to kind of be happening in combinatorial invariance is like, so for example, the following is, so in fact, all length 2 intervals in Bruhat order look like this. But if you look at the way that this is embedded inside Rn, this can be embedded in different ways. So it might be embedded in kind of this way, or it might be embedded as a square or a rectangle, or it might be embedded something like this. So my feeling about combinatorial invariance is somehow it's saying that we can like continuously deform between these different embeddings. So that one on the left kind of can be deformed into the one on the right, the one on the middle, and then one in the middle can be deformed onto the one on the left. But there's something funny going on here because the intermediate values have no meaning, never show up in the actual real world. So it's a little bit like something that we see in mathematics quite often, particularly in the last 20 or 30 years, where you have some structure which kind of comes from geometry or comes from the real world. And then you can move this structure a little bit and still it makes sense. Okay. So here's an example that like shows that this kind of naive deformation point of view really needs extra thought. This example kind of shocked me. So here's 2 intervals. So on the right, what I'm looking at is the interval from 0, 1, 2, 3, 4 to 4, 0, 1, 2, 3 inside S4. So if you know symmetric groups, this is like an n cycle. It's an incredibly natural interval to consider. And what I get if I look at this embedding is a hypercube, a 4-dimensional cube embedded inside a 4-dimensional space in a very, very natural way. Very important, this example, so I want it to be somewhat clear. So I take a 4-dimensional cube, I put it in a 4-dimensional space, and maybe I wiggle it around a little bit. The edges aren't parallel anymore and stuff, but basically it's a cube sitting in 4-dimensional space, which is where a cube should live. I hope you agree. Like a 4-dimensional cube should be in 4-dimensional space. Yeah? What's happening on the left is I have an isomorphic graph. And also, if you look at these 2 graphs, it might look initially like they're not isomorphic, but they are, okay? There's a simple, like I couldn't draw them in a way that they're obviously isomorphic, but you just wiggle them around a little bit, they're isomorphic. Okay? Take my word for it. These are 2 isomorphic intervals. And now I can look at the way that the one on the left is embedded, and it's embedded inside R3. So it's like I've taken a photograph of a 4 cube and drawn that photograph inside R3. So if you want an analogy, you know, here's a perfectly good cube living inside R3. But I could also take this cube, take a photograph of it and put it inside R2, as I've done. Yeah. Okay. And yeah, that's a big issue for my deformation philosophy. Yeah. So, and this kind of happens all the time, that you have some like very beautiful object and it looks like it should sit in dimension 12 and it's sitting in dimension 9 or something by some like horrible squashing procedure. And somehow you have to work out how to unsquash stuff, free it, and then prove the conjecture. Okay. Oh, I already wrote my analogy down the bottom. Okay, so that's why I think this conjecture is both hard and fascinating. Okay, so this is the point of the talk where I could finish. I just want to give you an optional extra on a little kind of aside on Bruhat intervals that I think is fascinating. So this will just take a few minutes. So I hope you've all met what a simplicial complex is. So a simplicial complex is formally just a set of subsets of a set such that it's closed undertaking subsets. But informally, it's a way of gluing simplices together to make a space. Okay, so on the left, I've drawn, so I have 4 vertices and I have 1, 2, 3, 4, 5 edges and one 3 simplex. And the corresponding simplicial complex just gives the subsets which span simplices on the right-hand side. That's what a simplicial complex is. Whenever I have a simplicial complex, I can take simplices, glue them together, form a geometric object. This is called the geometric realization. So given a post set, we can consider the set of chains. Okay, so this means in my post set, I start somewhere and then go up, 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 up. This gives me a subset of all vertices of my post set. And obviously, if I take a subset of a chain, that's still a chain by transitivity. And so I get a simplicial complex, which is called the order complex and is important in combinatorics. So just a simple example of why this is important. Essentially, the Möbius function, which is something which I hope you've met, is the Euler characteristic of the order complex. So the order complex is an important kind of topological invariant of posets. So we have this beautiful Björn-Vaks theorem, which tells you that the order complex of the open interval in Bruhat order from x to y. So I take the interval from x to y, and I delete the bottom and the top. I look at the order complex of that. I take its geometric realization. This is a sphere of dimension length of y minus length of x minus 2. So before I said that all intervals in Bruhat order of length 2 look like this. Okay. What's the proof of that? Well, the only simplicial complexes that are 0 spheres consist of 2 points. Yeah, there's no interesting way to construct 0 spheres. Another nice example of this is there's also not that many ways to triangulate S1. So the only ways of triangulating S1 are like this. And so basically that says that when I'm trying to build the middle of an interval of length 3, I kind of have to go up and down and up and down and up and down and up and down and up, and then I get an n crown. So I don't know the true meaning of this theorem. It's very nice. There's a more interesting formulation of this due to Björn, which basically explains that Bruhat intervals give rise to regular. So yeah, maybe I'll just say that very briefly. So out of the Björn-Vaks theorem, you get for any Bruhat interval, you get a triangulation of a sphere. So that's interesting. But Björn has another theorem which says that out of a Bruhat interval, there's a regular CW complex of a sphere such that the barycentric subdivision of that is this triangulation. So there's a more basic regular CW complex decomposition of the sphere giving rise to the Björn-Vaks theorem. So yeah, I don't really know how to make sense of this theorem, but it's interesting and it might be a clue. So thanks a lot. We've lost. Where did they go? Whoops.
Looking for the Hawaii hub.
Yeah.
Let's see if we can find them.
Okay. Oh,
There we go.
That's fine. So are there any questions from Hawaii?
I have a question. Can you hear me?
Yes.
Yesterday, did we resolve why the Kazhdan-Lusztig polynomials that evaluate to 1 are these smooth elements? Are those one and the same? I think you kind of referred to that today again.
Yeah, so I think, so on the exercises, I was just saying kind of, if all Kazhdan-Lusztig polynomials are 1, then I called that element smooth. This was just a definition. Yeah? But the reason that I'm doing that is that it's very close to the concept of the corresponding Schubert variety being smooth. And that we'll discuss tomorrow.
Okay.
So at the moment, like in the exercises yesterday, smoothness is just a definition, seems a bit arbitrary. But I hope it'll make more sense tomorrow, where it's really interpreted as the smoothness of an algebraic variety. Well, not quite, it's the rational smoothness of an algebraic variety, but it's basically the fact that, yeah, I won't overcomplicate it at this stage, but that's the idea. So the statement is that a Schubert variety, so using the theorem that I stated today of Dyer and Carroll, it tells you that the Schubert variety is kind of almost smooth if and only if the corresponding Bruhat graph is regular when we forget the edge directions.
Thanks.
Okay. Are there any questions from Brisbane? Doesn't seem to be the case. So have fun with the exercises.